Hey, great question. When you're when you're thinking about what is the derivative fundamentally, you'll often be presented with this, which is, of course, the limit definition of the derivative, but this can be very confusing. So basically, what others have said here is correct. The idea is that what is the rate of change of a certain function at a specific point? So specifically, the way I think of it is if you increase the input, whatever that is, a tiny bit, how much does the output increase? And then you take the ratio of that. That's fundamental, and that's the rate of change of the output divided by the input. That's fundamentally what the derivative is. Now, when you look at this definition, just in general, obviously the input is x, the output is f, but that could be anything like, input of time and output of distance, or input of position and output of temperature. It could be anything in physics, and you can measure how much does the output change if we increase the input by a little bit. But fundamentally, this definition, the way that I like to think about it, it looks really complicated when you look at it, but basically it's really just delta F over delta X, right? Like this right here, and I'll explain this in a second. This is really just a clever expression for delta F over delta X. So like if I share my screen, for example, or let me go through here. Like when we're looking at the actual limit definition of the derivative, you can see here that they've abstracted it so that if you start at a certain X value, and you have a certain h, or h is the same thing as delta x, that would move you to the right by a certain amount. And then you would have another point on your curve, which would have an input of x plus h, or delta x, whatever you want to call it. And then the function evaluated at that output. And if you think about it, this distance is really like y1 minus y2, f of x plus delta x minus f of x. That's y1 minus y2. And then this right here, like delta x, or just h, is x1 or x2 minus x1 from algebra. And the slope would be y2 minus y1, which is this, over x2 minus x1. So in other words, what we're really starting with is this is really just representing the slope of a secant line, right? So it's basically, just the slope between any 2 points on a curve for a general x value. And here we have the limit as delta x goes to 0. So essentially what happens, and you can see this, let me share again, that as I decrease h, which again is another way of writing delta x, as I increase that, you can see that forces the second point to get really, really close to the first point. And as you do that, again, you can't let it equal 0 because then you'll get an undefined answer, but you can take the limit as it approaches 0, and you can see what's happening. It's getting really, really close to the slope of the tangent line at that point. So that's why a secant line, which is the original expression, y2 minus y1 over x2 minus x1, if you take the limit as delta x, the gap between them shrinks to 0, it approaches the tangent line at that point. So that's really what's going on here. All of these things is like the delta f over delta x is really just rise over run, or the slope. So another way that I like to think about the derivative after you have a graph is it's really the slope on the graph if you zoom in really close around a certain point. So let me actually share another animation that I have. So if you look on this graph, for example, this is the graph of y equals x squared. And it doesn't make sense to say that this curve has a slope, right? You have to be a straight line to have a slope. But here's the key idea. If you pick any point on this graph and you just zoom in a million times, like zoom in infinitely, it's going to start looking like a straight line. This is kind of like how the planet Earth is spherical, but when you walk outside, the ground is flat. It's like if you zoom in on a curve enough, it starts looking flat. And now that it looks flat, now we can ask what the slope is. And if you look at the big square, it looks like we're going up 2 and over 1. So the slope would be 2 at this point. That's just at this point, though, to be clear. And by the way, that's what the tangent line represents. When you're talking about the tangent line, that the point tangent to the curve is basically what it looks like the slope is if you zoom in a million times. It just has it zoomed out, so you can see that. But if I go to a separate point, so like 0, let's say, and then if I zoom in infinitely here, you can see that eventually the curvature goes down and it looks like I have a completely horizontal line. So the slope would be 0. That's fundamentally what the derivative is. It's like if you zoom in infinitely, what does the slope start looking like? This expression just gives you a way to calculate it efficiently. So like if you had like f of x equals x squared, if you actually use this definition, and it's not easy, but you could do it, you could get at the end, you could calculate a function, 2x in this case, that would tell you the slope at every point. But this is fundamentally what it is. Hope that helps, and have a great day.